Hello, welcome to the 1.8 notes. These are on the squeeze theorem. I'm going to go real quick over and kind of the concept of the squeeze theorem, a real world situation, and then we're going to look at the formal definition, which is our second little slide. So here is our example we're going to look over to illustrate the concept of the squeeze theorem. So let's say that we have a cross country team, and during races, cross country races, Josh runs at least as fast as Carl. So he's always going to run at least Carl's pace or above. And then say we have another student, let's call him Jay Sean. And Jay Sean is going to run as least as fast as as Josh. So that's this idea in words, but if you were to represent this with math, you would say that Carl is always going to be slower, but could equal Josh's speed. And then Jay Sean is our fastest. So, because he is at least as fast as Josh, Josh is at least as fast as Carl. So this would be Carl's speed, Josh's speed, and then Jay Sean's speed. So let's say on this particular day, they're at this race and Carl runs a little bit quicker than normal. And Carl runs this 5K in a 16:30. Okay, and then on this particular day, let's say that Jay Sean runs a little bit slower than normal. Jay Sean also runs this 5K at a 16:30. Well, we know that Carl's speed is always less than or equal to Josh's, which is always less than or equal to Jay Sean. So since Carl's speed is 16:30 and Jay Sean's speed is 30, then what has to happen is that Josh's speed also has to be 16:30, because that's the only value that would fulfill both of these things, because it's got to be equal. That's the only way that this statement would be true, that Josh's speed would be in the middle of Carl and Jay Sean, is if it equaled that. And so that's the idea of the squeeze theorem. The idea is if you know information about the lowest bound and the greatest bound, and if those two things are equal to each other, that means that this middle data point has to equal the lower and the greater. So that's kind of like a big picture definition. Let's look at the mathematically proper definition. Also a big idea, I don't know if I have this on the first slide or the second because I edited this, but tables and graphs will always approximate limits, but algebra and then the squeeze theorem, which is a form of algebra, can prove a limit must be true. So what this says is if f of x is less than g of x, which is less than h of x for x near a, except possibly at a, and the limit as x approaches a of f of x equals the limit as x approaches a of h of x, and they both equal L, then by the squeeze theorem, the limit as x approaches a of g of x also equals L. So this is true if f of x is less than or equal to g of x, which is less than or equal to h of x. If these two limits have, or if these two have a limit at L, then this also would have to have a limit at L. I'll give you kind of a physical example. So I'm going to make f of x red over here. I'll make g of x purple, and then I'll make another color. Let's do blue. H of x purple. So in this illustration over here, we're going to approach a, and then we're told that the limit of all of these things is L. So let's look at f of x first. So f of x is going to look like this. Let's say it looks like that. We'll do h of x next because h of x is the largest one. Say that h of x looks like this. And then we already knew that g of x was squeezed between them. And it would look something like this. And because the blue and the red function are the same at that place, and that means because g of x is between them, that it would also have to have a limit of L. And so the function basically squeezes between the outside functions at a specific point, making the limits equal the same thing. So the big conditions for the squeeze theorem to work is that there has to be like a order to the functions. One has to be less than one, which has to be less than the other. And then the two outer ones, so these two guys right here, these two outer ones, their limits at this point have to be the same. And so this next couple slides is going to say, ask us questions like, does the squeeze theorem, can you actually use it? And so what we would be doing for this one right here is, it says, example 1, g of x is less than f of x, which is less than 3x squared for all x. Are you able to use the squeeze theorem to find the limit as x approaches 2 of f of x? If so, find it. So our goal here is to see if the limit here at 2 and the limit here at this function, are they the same thing? And if they are the same thing, then we can use the squeeze theorem. So basically what I'm trying to figure out is the limit as x approaches 2 of g of x, or of gx. We're trying to use that to help us find this middle limit. So I can just use, since I know what the function of this bottom one is, of the lower bound, I can just plug in 2 here. And just using direct substitution, I get a finite limit, so I have my answer. And I can also just plug in 2 here. I'm going to get 12 is less than or equal to the limit as x approaches 2 of f of x, which is less than or equal to, well, 2 squared is 4, 3 times 4 is 12. And notice these lower and upper bounds are the same thing, and it says 12 is less than or equal to the limit as x approaches 2 of f of x, which is less than or equal to 12. The only thing that this middle function, the only limit this middle function could have that would fulfill the lower bound and the upper bound would be 12. And so by the squeeze theorem, and you have to write this like on your when you take test and like AP test too. So by squeeze theorem, the limit as x approaches 2 of f of x equals 12. So like if this one had been like 16, right, you could not have used this because the lower bound and the upper bound were not the same thing. If, say, it had said 6 of x is greater than or equal to f of x, which is less than or equal to 3x squared, well, that doesn't work because both of those functions are less than f of x, so that doesn't fulfill the requirements for the squeeze theorem. So let's go on to a new one. This has a lot, but we're just going to take it. It looks a little bit more confusing than it really is. So it says the function f of x equals cosine of 1 of x times sine x cubed minus 1 divided by x to the 4th power is bounded below by g of x equals negative square root of 1.11 minus x squared, and from above by h of x equals the square root of 1.11 minus x squared. Sorry, I didn't say this out loud, but this one has a negative out front. On the interval, -1, 1, is there enough information to determine the limit as x approaches 0 of cosine of 1 of x sine x cubed minus 1 divided by x to the 4th power? So that looks really overwhelming, but let's just first think to use maybe the squeeze theorem. And so anytime it gives you like more than one function like this and it asks you to find the limit of one of the three, that's kind of a good indication to use the squeeze theorem. Another thing that indicates to me that I need to use the squeeze theorem is this language, is bounded from below and then from above. So that kind of tells me, okay, well, we're going to use our inequalities there. And so that's another hint to tell me that I should be using the squeeze theorem. And so first thing, what we know based on this is that below f of x is g of x, because it says it's bounded from below, and then bounded from above by h of x. So we know that this is true. And so for the squeeze theorem to work, we know that that's true, so that's great. For the squeeze theorem to work, the limit as h of x approaches g of x, like this is the fact that needs to be true in order for the squeeze theorem to work, is that the limit as x approaches 0 of g of x has to be the same as the limit as x approaches 0 of h of x, because this function f of x would be like what was in the middle. And so if we wanted to figure that out, these two things had to be true. So let's go ahead and try to figure that out here. If we were to find the limit as h approaches 0 of g of x, we are going to plug in 0 for this function up here. So I'm going to do negative 1.11 minus 0 squared, and that equals negative 1.11. I'm going to leave it like that. And then I need to find the right bound to and that I would plug it in 1.11 minus 0 squared. The big difference is there's no negative sign outside the square root, and that gives us positive 1.11, and those are not the same thing. And so because they aren't the same thing, we can't use the squeeze theorem, because you have to have the limit of those outer bounds be the same thing. So I'm going to write the squeeze theorem cannot be used because, and I can just write it like this, the limit as x approaches 0 of g of x doesn't equal the limit as x approaches 0 of h of x. So that is why it does not work. Okay, so moving on. The squeeze theorem is a strategy often used to help us find the limit of trig functions when trig identities don't help. And I'll show you some examples of why like trig identities wouldn't help on the next page. But in order to actually use the squeeze theorem with trig, we have to remember one thing about these popular trig functions. So this is the function right here. This is the function of sine of x. And this is a function of cosine of x. And one thing that we need to remember is the range, which is how high and low the y values go. So if you zoom in here, none of the y values ever go below -1, and they never go above -1. And so if you were to write the range out, you would write -1, 1, and you put them in brackets because sine of x could equal -1, or it could equal 1. And this is going to be true for any function of sine that doesn't have any vertical that doesn't have any like up or down translations or any dilations on the outside of the parentheses. So like this is going to be the range for sine of 3x or sine of 1 over x, but it wouldn't be the range for like sine of x plus 3, because this would translate this whole function up 3 points. But as long as the change and the adjustment is within the parentheses, it's not going to change the range. And the same thing for here is this range down here is -1 to 1. Another thing to think about, another way to think about this right here, is that this falls between, and this is going to come on the next page, it falls between y equals 1, because that's technically what that line is right here. And it falls between y equals -1. And that's the same thing for this cosine function. It falls between y equals 1 and y equals -1. And we're going to come back to that on the next page, but that's important for these functions. So continuing on, it says use the squeeze theorem to find the value of the following limit. So why do I know to use the squeeze theorem here, not anything else? Well, the reason I'm not using trig identities for this, a big clue is this right here. There is no, like if you look through all of the trig functions and all of the identities, I'm going to print out a little list for you and to look through them. None of them have anything like cosine 1 over x on the inside of it. There's nothing that you could replace that with to make it help us cross anything out. There's nothing you could do to help us cross out the x that's causing the problem. The reason you can't just plug in 0 right here is because you'd have cosine of 1 over 0, and you can't divide by 0. And so that's the reason why you can't just like plug in 0 here. And so that's how you know to use the squeeze theorem here, is because there's some problem in the cosine function that's within the cosine function, not outside of it. And so this is how we're going to do this. So we know, we just talked about this, that cosine, like normal cosine, always falls between y equals -1 and y equals 1. We also know, based on what we talked about, that cosine of 1 over x, that wouldn't translate it up or down or make it bigger or smaller. So that cosine of 1 over x is also between -1 and 1. Well, we're going to do some like weird multiplication here, but it's going to work. This doesn't really help us find the limit of this because this has an x squared. But what if I use just my properties of solving equations that I know, and I multiply everything by x squared? As long as I do it on all three sides, it'll work. It won't change the value of anything. So I'll get -x squared is less than or equal to x squared times cosine 1 over x, which is less than or equal to x squared. And notice that this area here now matches that. So say I was going to go and find the limit of these things. Okay, well, I can't plug a 0 in the middle. We already knew that. But if I plug in 0 in for this function, I'm going to get negative 0 squared. Negative 0 squared. If I plug in 0 to that upper bounded function, I would get 0 squared. And both of those come out to be 0. And so since our lower bound is 0 and our upper bound is 0, and because this function is just squeezed between them, then by the squeeze theorem, the limit as x approaches 0 of x squared times cosine 1 to the x power equals 0. So, go on to example 4. I'm going to kind of work it out quietly, but it's really almost exactly the same as example 3. And a lot of times, but not always, these problems that involve the cosine 1 over x or sine over 1 of x come out to be 0. But it doesn't always happen, but it just is like often. So for example 4, I'm going to work through this quickly. But like I said, but this is the same idea that sine of x is bounded between y equals -1 and y equals +1. If I were to multiply everything by x to the 6th power, you get negative x to the 6th power, which is less than or equal to x to the 6th power sine over 1 over x. X to the 6th power, and I get negative 0 to the 6th power. Oh, sorry, I gotta find the limit. And again, the reason why I can't just plug in 0, the reason why I can't just plug in 0 right now is because you can't divide by, like this would be a problem. You can't do 1 divided by 0. That's the problem. So by the squeeze theorem, I know that this helps us. Okay, if I were to plug in 0 here, I would get 0. Because negative 0 to the 6th power is 0. And then if you plug in 0 to x to the 6th power, you get 0. So again, by the squeeze theorem, the limit as x approaches 0 of x to the 6th power sine 1 over x equals 0. And that is your answer. That's kind of how you need to justify it. You need to say by the squeeze theorem to know that you're not just like making up math. Okay, our last example is really quick, and we've already kind of talked about this in class. This was what I mentioned, like you just can know this, but the squeeze theorem provides us with two popular limits. You can memorize these, and I said we will watch the proofs of them later. If you would like to watch the proofs of them, they are on Khan Academy, but you do not need to know the proofs. But one thing, if you were to watch the proofs, and the way that mathematicians figured this out is they use the squeeze theorem. But the limit as x approaches 0 of sine of x divided by x is 1, and you can just use that whenever you want. And the limit as x approaches 0 of 1 minus cosine of x divided by x is 0. I need to check on that. Let me check on that real quick. But you don't need that one for the next one. Hold on. I'm just Googling it real quick. You can totally skip this laggingness. I just want to make sure it's not 0. Or that it's not 1. Okay, it's 0. I just doubted myself for a second. Okay, so that one is 0. So those are pieces of information you can always use. Example 5 is the last example we're going to do, and you actually did do this in class the other day. It was in one of those like calculated worksheets we did, but there's no like trig identity that I know of that would help me cancel out just a solid x. And so if I plug in 0 right now, I'm going to get tangent of x becomes sine of x over cosine of x. This is kind of what you have. If I plug in 0, I'm going to get 1 over 0, and you just can't divide by 0. You're divided by 0 twice, so that doesn't work. So what I'm going to do is I know that I can't get rid of x, but I'm going to see what else I can do. And I know that tangent of x breaks down to sine of x over cosine of x. And so that's really my only hope. And now I have a fraction divided by a whole number. So to help myself, I'm going to turn this whole number into a fraction. And now I'm going to use my dividing fractions techniques, and I'm going to keep the numerator, change this to multiplication, and then flip the denominator. And if you were to look at this, based on the commutative property of multiplication, I can move stuff around. So I'm going to change this to sine of x over x, and I'm going to just move, kind of basically switch the places of the x and the cosine. Based on some algebraic properties, we can take these two limits separately if we want to. We can break them apart because it's just multiplication. And we know by the squeeze theorem that the limit as x approaches 0 sine of x over x is 1. Something we can memorize, and then we can just plug in 0 now for cosine of 0. And this will give us 1 times cosine of 0 is 1. So I'll get 1. And that's the answer. And sorry, up here, the problem was that this was 0 over 1. So this part up here, if you're looking here, this, I said it wrong, but you're still divided by 0. You just tangent of 0 is 0, not undefined. So, but the big idea is the answer here is 1. So if you have any questions for me, let me know in class or send me an email, and that's all we have for the squeeze theorem.